And I'll be doing a presentation today on Monte Carlo expectation maximization. Uh, Chose this topic because it was an extension of something I had a really tough time understanding in Module 3. So I wanted to really solidify my understanding of base EM and then hopefully take it to the next level. So this is kind of an outline of what we're going to go through. We've got introduction. I'll introduce some terms. We'll do a review of some of our uh, foundational technology, our processes. Then we'll go through the specifics of the Monte Carlo expectation maximization theory. We'll go through a generalized example. A conclusion, and I'll provide you a list of references. So let's start here with the introduction. So what again is Monte Carlo expectation maximization? Also, going back to the seminal paper, it is a mechanism that allows us to complete maximum likelihood estimates when we have incomplete data. And okay, and well, so what's this, the MC thing on the front of it again? Well, that's the Monte Carlo expectation maximization that was really formulated in 1990 as a mechanism where they could do Monte Carlo simulations in lieu of actually having to do actual other tests. So hence this poor man's algorithm. So why do we need this MCM rather than just EM? You know, what's it get me? So the big thing is that in addition to keeping from having to do these other additional samples here, there's other times where it's analytically intractable to sample. And the Monte Carlo methodology enables us to do this with an alternative process. So, and then what kind of problems do we use on? Well, essentially anything that's in the range for expectation maximization. You could also use the Monte Carlo methodology on it as well. So let's do a review of some of the core technologies that are involved. Get straight here. Okay. And honestly, a lot of this was just to help me keep level set in my mind of what we're really trying to do. So I've got here notes on expected value 101, just basic things with respect to a continuous distribution versus a discrete distribution and what that means. And we've got conditional probability, talking about how we take the intersection of those, and then to find the conditioning, we actually take the do some division here as is expressed. Then a review of marginalization. This is quite important. It talks about when we've got uh, uh, data that's kind of broken up, well, how can we find things about different conditional distributions on that? And so this is just kind of a simplified example. It's like, well, if we want to find out, what are the probabilities of it going to be hot, we also have this weather piece of it. Well, we can just add those two up. And then, moreover, take into, so that's a univariate case. And then it's multivariate. It's like, well, what if we wanted to find out, if it's sunny, we could actually sum across all these things that are highlighted. Again, a lot of this is just a review of some of the things that are key to being able to perform both expectation maximization, then Monte Carlo expectation maximization. And then just a quick reminder of what Monte Carlo expected value is, particularly for uh, uh, definite integrals. It's a way where we can do a sampling across the interval and then just do the arithmetic average of that function to actually come up with an approximation. Now we do a quick review of, well, so what's EM again? I've got some stuff from the 1990 paper as well as from the actual lecture. In the 1990 paper, it is talked about you've got observed data and missing data, and then in our lexicon, we've got it as we also have the additional variable of y to represent the complete data. So this gets to the graphical representation of the iterative nature. If we had some data and we had some distributions, but we didn't know what the parameters were, it's a mechanism where we can go through and adjust the parameters and redefine like the fit, and we keep iteratively going through this until things stabilize, until our delta has sufficiently uh, reduced that we can say this is a good estimate for the parameters. And then just EM overall using the lexicon from Module 3. Um, we've got the likelihood, but want to address it uh, indirectly instead of directly. So this goes through just a lot of the stuff that was out of the class notes. First, we come up with we fill in our missing data based on our observed data and estimated density parameters. We come up with this, and then we re-estimate that based on the complete data, uh, which is X observed and Z missing. More formally, have this down here. We have our Q function that talks about the expected value, and we take this through and expand it into our integral, kind of as we had looked at up there before in the expected value 101 with the expected value of a continuous distribution. We get our Q, and then after you go through all of the work of developing this, then the actual algorithm itself is straightforward. We have an E step, and then we maximize that expectation to come up with our formula, and then we just keep iterating on those um, estimates of the parameter until we're below some threshold of delta. All right, that's just basic EM. So let's go to MC EM. So this is a summation of three different papers and lecture notes, essentially saying that the same thing here, that and I've done some normalization so that you know, X means observed data across the board, uh, and then Z means the uh, missing data across the board. Looks like I might have missed one there, but oh, no, missing and unobserved are synonymous. Um, what it's saying is uh, instead of doing that integral, we can actually compute that E step with a Monte Carlo estimation. So that's what's expressly illustrated right here. Okay, and all three of these papers are essentially saying the same thing. This more generally, Monte Carlo sampling methods can be used to approximate the expectation set when it's not easy to compute it analytically. And that's what we're focused on. All right. Now let's go over to the generalized example that I'd worked through. And this one is actually inspired somewhat from the midterm, a little bit from one of the lecture notes from one of the professors. and partly from the seminal EM paper from 1977. And in this, we've got, and I'll go through the kind of the theory first, and then we'll go through a little bit of the implementation. So we've got uh, N textbooks, total of N, and there's four categories, and that first category can actually be subdivided further into an X1A, an X1B, and we know that the total of these is N, and furthermore, we know the total of X1, X2, X3, and X4, but we don't know what X1 equals or what X1A equals or X1B equals. So we've got this first equation here, just saying they sum up to n. Then we're saying they have the associated probabilities of being in each category as expressed here, notionally. So if it's in x1a, it's in a half. If it's in x1b, it's a known parameter over 4, etc., etc. And this is just note that it is a valid probability. It does sum up to 1. So as we progress through here, we say, well, let's take a look at our complete density. And it's a multinomial. And we just have this expressed here, standard multinomial form. We take the log of that, and then we can drop any term that doesn't have the parameter theta in it. So we can drop this guy, drop this guy. We do a little bit of algebra, and we come up with this likelihood. And we can say, oh, well, all right, well, the next step should just be to take the derivative, set it to 0, maximize. But wait a second, we don't know what these values are. So this is not going to be a path that we can immediately progress on particularly well. So let's take an alternative approach and kind of recap what our observed data is. So that's the x1, x2, x3, x4 over the four categories. Z is our missing unobserved data. So that's the subset of x1, so x1a, x1b. And then we have our complete data. Going to the EM lexicon equation, we attempt to write that full expected value here, which is expressed this way. We do a little bit of manipulation to express the expected value of the large and the marginal density of the complete data, y here, given our observed data x. And say, okay, well, let's, instead of doing this, let's see if we can do a Monte Carlo expectation to solve solve this Q, and use a simulation of Z from our conditional marginal density with respect to our unknown data. And we borrow some of the algebra up here from equation 5, so that we can take random samples of this binomial with these parameters to come up with what we're going to plug into the next equation. And this is our actual E step. And just kind of the standard MCEM or the standard E step, we go through here. We can then maximize that M step. We can maximize the E step in the M step, and then we can compute our next theta. And once we've got that equation, we can just iterate until our delta is below a certain value, and we say that's the estimate. All right, so let's take an attempt now at looking at a concrete example. So we do some initialization. We say we're going to have 350 in the first, 350 books in the first category, 200 in the second, 100 in the third, and 300 in the fourth. Come up with a total count. We do our initialization for our Monte Carlo. We go ahead and set our theta naught. 2.2. And then we go ahead and we set up our sampling here. So this is that binomial sample with the x1 and the probability. And we do 10,000 samples here. We've got our functions to calculate the term and then to do our sums. And then we actually just go ahead and do that. And now we've got an E-step here. That looks great. Unfortunately, something went wrong with this particular logic as I attempted to work through it. And this is unfortunately the end of the concrete example and just leaves it as an abridged sample. The reason I say this is have this happy little emoji here is our E-step is not something that can be maximized, and it actually must be maximized if we go back up here and take a look at this. It has to be maximized so we can come up with that next theta plus one step. So there was either a misinterpretation on my part or a math error, more likely a logic error for this one. But if I'd corrected that, we'd be able to go through, establish our equation, do our iteration, and then watch the graph kind of settle down into a particular estimate. All right. And a couple items here just to conclude the presentation. So in general, need to be aware of Monte Carlo error. You're making simulations, and there's quite a bit of research on how that can oftentimes bite you. And then particularly here, I've got one called out with the between simulation variability called Monte Carlo error. Um, Moreover, or another one in that same vein, oftentimes for simple models, we can use Monte Carlo just fine, but for more complex models, we might have to use other things like importance sampling, which we went over earlier in the class. Some other um, potential applications of this. We've got ascent-based MCM, which attempts to optimize the overall process by making sure we're always going in the same direction. Sounds very similar to our ascent-based algorithm early in the class as well. And I've got some samplings here from what that looks like in a formal sense. And kind of close out. So I made the assertion early on that anything with EM is also potentially another use for the MCM process as well. So that includes things like disentangling superimposed signals, uh, mixed Gaussian models, hidden Markov models, estimating parameters from Dirichlet, and finding optimal integers for fixed models. So in conclusion, we've gone through a review of the component parts, or a review of expectation maximization as a standalone, overview of Monte Carlo expectation maximization, and an attempt at a concrete sample problem with a little bit of an epic fail. But it's all good. Quick overview of the references. We've got these here. And I will list I'll post both the references and the example write-up on the board as well. Thank you so much for joining, and been great having class with everyone. Take care.